Welcome back to physics classes. Legend says that the famous scientist Galileo Galilei worked in the Grand Pisa Cathedral where a huge chandelier hung from the ceiling. He noticed that the chandelier was swinging gently in the wind. Sometimes, when strong winds blew, the chandelier swung in the larger arcs. When the wind weakens, the swings became smaller. Galileo wanted to measure the time it took to complete one full swing, but in those days there were no stopwatches or timers. How did he do it? He used his pulse. With every beat of his heart, he timed the chandelier's motion. And then he noticed something surprising. No matter how big or small the swing, the back and forth motion always took the same time. It was extraordinary. Regardless of the amplitude of the swing, the chandelier always took the same time to complete one round trip. To study it further, Galileo began experimenting with simple pendulums, a small weight or bob suspended from a string. Through these experiments, Galileo discovered that the period of a pendulum is not only independent of its amplitude but also independent of the mass of its bob. The period refers to the time it takes for the bob to complete one full swing. Any motion that repeats after a regular interval is known as periodic motion or harmonic motion. A simple pendulum is an example of a special type of harmonic motion called simple harmonic motion. Oscillations in the spring is also another common example of simple harmonic motion. Usually, a spring will have a natural length, which we will call the equilibrium position. If you compress the spring and release it, it will execute a back and forth motion. Robert Hooke, a famous scientist, observed that the restoring force developed in the spring is directly proportional to the displacement from the equilibrium position. If y is the distance from the equilibrium position, then the restoring force F equal to minus ky, where k is a proportionality constant known as the spring constant. The spring constant k measures the stiffness of the spring. A larger k means the spring is stiffer, so it doesn't stretch or compress much. A smaller k means the spring is more flexible, so it stretches or compresses more under the same force. Minus sign in the equation indicates that the direction of restoring force is always towards the equilibrium position. To see the actual beauty of simple harmonic motion, we should look through the lens of mathematics. Let us build this in a step-by-step procedure. The maximum displacement of a spring from its equilibrium is the amplitude of oscillation. Let us call this point A. If we release the spring from this position, it will pass through the equilibrium point, go to minus A, travel through the equilibrium point and come back to A. This completes one cycle. The time it takes to complete one cycle is the period of oscillation, usually represented by capital letter T. Now, imagine a particle moving in uniform circular motion around a circle of radius a with angular velocity omega. If we project this particle vertically onto the circle's diameter, that projection performs simple harmonic motion. At any given moment, we can draw a right triangle where the radius is the hypotenuse and the vertical projection is the opposite side. Using basic trigonometry, we write sin theta equal to vertical projection by radius, that is equal to y by a. Since angular velocity is constant, angular displacement increases linearly with time, theta equal to omega t, which give us the relation y equal to a sin omega t. This equation represents the displacement of simple harmonic motion at time t. Now, we can easily find the velocity of the particle by differentiating the displacement equation v equal to dy by dt, that is equal to a omega cos omega t. Since velocity is described by the cosine of omega t, it is 0 at the ends and maximum in the middle. The acceleration, which is the derivative of velocity, is a equal to dv by dt equal to minus a omega square sin omega t. The minus comes because derivative of cosine is minus sine. But what is a sin omega t? It is displacement y. So the acceleration is simply a equal to minus omega square into y. Following displacement, acceleration is 0 at the middle and maximum at both ends since it is a sine function. The direction of acceleration is opposite to the direction of displacement indicated by the minus sign. Now let us bring it all together. The position of the mass follows a sine curve y equal to a sin omega t. The slope of the displacement curve gives velocity v equal to a omega cos omega t. This follows a cosine curve. The slope of velocity gives acceleration a equal to minus omega square y. Notice that acceleration is always directed opposite to the displacement, reaching its maximum at the extremes. These three graphs together captures the essence of simple harmonic motion. Displacement, velocity and acceleration are interdependent, perfectly described by sine and cosine functions. Now let us compare Hooke's law with the Newton's second law, F equal to ma. This means force equals mass times acceleration. We saw acceleration is minus omega square y. So F equal to minus m omega square into y. According to Hooke's law, the restoring force is provided by the spring and follows F equal to minus ky. Newton's law and Hooke's law is talking about the same force. Hence, minus m omega square y should be equal to minus ky. Dividing and rearranging, we get the equation omega square equal to k by m. This equation shows that the square of angular frequency depends on the stiffness of the spring and mass of the object. A stiffer spring or a lighter mass results in faster oscillation. To complete the discussion, let us calculate the energy of simple harmonic motion. A body executing simple harmonic motion has both kinetic energy and potential energy. Total energy is the sum of kinetic energy and potential energy. The potential energy U of y is the work done in displacing the object against the restoring force, which we find by integrating the force. U of y should be equal to minus integral f dy equal to minus integral minus ky dy equal to half ky square. Now, the kinetic energy is k of y equal to half mv square. Let E denote total energy, E equal to U of y plus k of y. That is, E equal to half ky square plus half mv square. By the law of conservation of energy, this total energy remains constant throughout the motion. So, the total energy at the maximum displacement and the total energy at the equilibrium point should be the same. What is total energy at maximum displacement? Y equal to a. Velocity is 0 at y equal to a. That means kinetic energy should be 0 at maximum displacement. So only potential energy term contributes to the energy. So total energy equal to U of a is equal to half ka square. What is the total energy at the equilibrium point or y equal to 0? Displacement is 0 at y equal to 0. So potential energy must be 0. All energy is kinetic in nature. So the body moves with maximum velocity. Let us denote this maximum velocity Vmax. So kinetic energy is maximum kinetic energy equal to half mv square max. By equating energy at both points, that means at maximum displacement and at equilibrium, half ka square equal to half mv mass square. Simplifying this equation, we can find an expression for maximum velocity, that is Vmax square equal to k by m into a square. That translates to Vmax equal to a into root of k by m. But root of k by m is omega, so we can write it as a omega. The velocity can also be expressed as a function of y. We will use the total energy at any arbitrary displacement y and equate it to total energy at the maximum displacement to find this expression. Half ky square plus half mv square should be equal to half ka square. Rearranging and solving for velocity, v square equal to k by m into a square minus y square, that is v equal to omega times under square root a square minus y square. The equations of HHM are mathematically simple but powerful. They allow physicists to predict system behavior with precision. SHM's ability to simplify and model diverse phenomena makes it an indispensable tool in physics and beyond. Not only the oscillations of springs and pendulum, many real-world systems can be approximated as simple harmonic motion for small displacements, vibrations of bridges and buildings, sound waves which are longitudinal waves modeled as SHM, seismic waves during earthquakes, vibrations of atoms in a crystal lattice and molecules in solids are all examples for this. Now, let us do a problem. A spider of mass 0.30 gram waits in its web of negligible mass. A slight movement caused the web to vibrate with a frequency of about 15 Hz. Estimate the value of spring stiffness constant K for the web. At what frequency would you expect the web to vibrate if an insect of mass 0.1 gram were trapped in addition to the spider? Next time you visit a nearby park with swings for children to play on, try this experiment. Select swings of different lengths and observe their periods of oscillation without anyone sitting on them. Do their periods depend only on their lengths? Now ask someone to sit on a swing. Does the period of oscillation change? The simple observation that Galileo made in a church sparked a powerful idea. He went on to design careful experiments and record the results with remarkable precision. Later, Robert Hooke too faced the challenges, but through persistence, he discovered the law that now bears his name. Together, their work, refined and expanded by known and unknown scientists, shaped our understanding of pendulums and oscillations. What began as the swing of a chandelier grew into discoveries that built better clocks, advanced science, and transformed the world. It is a reminder that even simple observation, guided by curiosity and persistence, explained through elegance of simple mathematics, can change the course of history. Thank you.